Hmm. Let's talk about graphing techniques using transformations now. The transformations that we have in mind are horizontal, vertical shifts, reflection, stretch, compression. The stretch and compression could be in either vertical or horizontal direction. So what we would like to do here is use the basic functions that we learned about earlier in the library of functions, and we're just going to move them around the Cartesian coordinate system. Now sometimes we simply shift them to the right, left, or up and down, and others you may indeed actually change or distort the graph. The graphs that are resulted using horizontal vertical shifts, these we call them rigid transformations because they don't affect the shape of the graph. But then there are non-rigid transformations. Those that cause a stretch and compression are non-rigid. So I'm just going to go ahead and write those for reference. These will be what we call non-rigid transformations. They're reflections and horizontal vertical shifts. These are rigid. Again, they maintain or preserve the original shape without distorting it. So what are we interested in? Suppose the original function is y equal f of x, whatever the function might be. Could be any one of the functions in our library of functions or any functions that we haven't talked about yet. Okay, so that's what f of x is, the original function. Now, anytime we add a constant to the original function, so I'm looking at plus k here. K is a constant. Now, depending on the value of the constant, if k is positive, then it causes the graph of f of x to shift up k units. And if k is negative, then therefore we're going to shift it down by absolute value of k units. The reason for absolute value here is necessary so we don't get into a double negative situation. Because when you say, for example, when I shift down -2, well, down -2 puts you kind of back up to where you were. Because with the word down, you actually make the movement. And then let's say down 2 brings you down 2. And then down -2 takes you back up to where you started. That's just to safeguard against double negative, the absolute value here. So a number plus or minus the basic function is going to cause a vertical shift. Okay. And this shift is going to be vertical. Now, sometimes we have in parentheses f of x minus a number. Now, the minus here, notice I use the red mark here for the minus. It's important to have it in the correct form. It has to be in the minus form, negative form. This will be an example of a horizontal shift. Now, this one is a horizontal shift. And the horizontal shift is going to be to the right if h is positive, and it's going to go to the left if h is negative. H units to the right, absolute value of h units to the left. And then we're going to look at the graph of y equals a. A is a constant, a non-zero constant, right? Because if you multiply by 0, then that pretty much gets rid of the function. So if we have a non-zero constant, a times f of x. Now, if the number that pre-multiplies the function, this number a, if it's negative, a less than 0 means negative. If that number is negative, then the effect of negative is to cause a reflection about the x-axis, the original function. You simply flip it over about the x-axis. If absolute value of a, now here again absolute value means negative, positive, doesn't matter. We think of the magnitude of the number. So if absolute value of a is 1, the magnitude of the number is between 0 and 1, then that will cause a vertical compression of the graph by a factor of a, absolute value of a again. If absolute value of a is positive, then we have a vertical stretch of the graph of the function by a factor of a. Okay, and the next one is going to be f of negative x. This time we have negative inside parentheses. So we change x with negative x, in other words. This will cause a reflection of the function about the y-axis. And what if the a, remember up here a was on the outside, what if a moves inside? If a is inside multiplied by x in the function? Well, again, depending on whether a is positive or negative. If a is negative, remember the negative part we attribute to a reflection if a is negative. And we already mentioned that negative causes a reflection, so it's okay to think of a as positive now. So for example, if I have f of negative 2x, well, the negative part causes a reflection, and then I just think of f of 2x and see what 2 does to that function. Notice again, the value of a is inside parentheses, not on the outside. And if a is positive here, depending on the value of a, so a between 0 and 1, like 1/2, 1/3, 1/4, 3/4, then there will be a horizontal stretch of that the graph of the function by a factor of 1 over a. And if a is positive, then you have a horizontal compression by a factor of a. Now, of course, through examples, I'll show you how these work. Now, one thing I want to, first of all, make sure we get this straight. When we talk about f of ax, that does not equal to a f of x in general. Okay? In general, there are some cases, and I'll show you an example, where actually a can be brought outside, but not in general. Keep that in mind. A is not a factor that we can bring outside. Okay, so that's definitely not true. All right. So let's take a look at some examples. Now, in my examples, I'm going to start with something simple. And remember, we're just going to use our basic functions that we had in the library of functions. So let's take a look at our first example. In this first example, suppose h of x is equal to square root of x plus 2. Now for this one, f of x, the basic function is the square root function, correct? And the basic square root function is going to look like so. Again, these are functions in our library of functions. We've already talked about these in previous lecture, lecture 4. Therefore, what I'm looking at here, x plus 2, I can think of this as f of x plus 2, correct? In here. If I look at f of x plus 2, remember we replace x with x plus 2, so you see I get what the function is. That's what h of x is, correct? Now this x plus 2, I can actually think of this as square root of x minus, and then we go with negative 2. The double negative on 2 makes it positive, so I haven't changed the function. So I have square root of x minus negative 2. Again, the key is to have it in this form. Now what we're looking at here, indeed, I'm looking at f at x minus h. So the function that I'm working, I can adjust it for that, and I'm going to be writing it as x minus 2. Okay. And this way, the reason I'm doing this because I need to identify h. So it looks like h is negative 2, correct? So my h is negative 2, which is less than 0. Therefore, this is going to move to the left 2 units. Or it's going to have a horizontal shift of 2 units to the left. And you can match it against this case right in here. Okay, so for f at x minus h, if h is less than 0, then you have absolute value of h units to the left. All right, so I can actually now graph this function rather easily and quickly. So here's where 0 is. I'm going to move to the left. This is negative 2, and then I'm just going to graph this. There you have it. And this is going to be square root of x plus 2. and that is the graph of that function. Okay, and there we have this example here. So I'll show you now another example. Well, before I do another example, actually, here's another way that we can do this quickly without going through maybe all of this. And going through this was interesting, is good because that's really what's going on. But here's how else we can do this. If you think about in terms of graph of the basic square roots, remember that square root of x starts at 0, right? Right in here, 0. So if you think of the radicand and think about what makes the radicand 0, so I get 0, because remember that point is x0, y0. So I want to see how can I make this radicand 0. Well, x plus 2 must be 0. That means x is negative 2, right? 1, 2. So here's negative 2. So what makes the radicand 0 in the square root? And then redraw that. In other words, your point 0, 0 is now moved to negative 2, 0. So that 0 is here now, the 0 for y. That would be another way to do this. And finally, another way that I usually tell students is this. The move to the right or left. I'm trying to clarify this portion now. The move to the right or left, this h negative 2, that's always going to be x plus 2, set it again, equal to 0. X is negative 2. Then negative 2, what makes this 0? Negative 2, that is the value of h here. Okay, so again, those are a couple of ways that we can do this without going through and setting it up the way we did. Now let's finish this. In fact, let's also write domain and range for this. So domain of h, the function h is going to be, remember, domain is all possible x values. Okay, so for domain of the function, you pretty much look at this. You see that? Everywhere I go on x, that's the graph. Anywhere on x, I can connect to the graph. So that happens from negative 2 to infinity. And what is the range of the function? Our function is h, the range of h here. For range of h, we look at the y-axis, right? So this time now I'm going to project to y-axis. You see that? And again, although gradual, but this eventually works its way to infinity. So it looks like the lowest it can be is 0. And the highest is infinity along the y-axis. All right, and there we have this one. We already graphed it here, so I'm gonna, that's fine, we'll leave this here. And here's h of x. All right. This is called graphing using transformations. Now let's do another example. In this next example, let's do a simple graph of f of x equals, this time, negative cube root of x. So our basic function, we recognize our basic function is the cube root function, correct? And this is what the cube root function from library of functions looks like. The effect of negative, so this would be, I can think of this as a f of x, where a is less than 0. In that, indeed, a is exactly negative 1. That's going to cause a reflection, right? A reflection about the x-axis. So this part reflects down here. This part reflects up there. The part of the graph that's in the third quadrant actually now appears in the second quadrant. And there we have it. The red is the graph of the function, negative cube root of x. That's what this is. And the good thing about transformation, you can actually track the function and see how it works, how it actually eventually shapes itself into the final form. The domain of this function, x can be anything, negative infinity to infinity. Again, you see that anywhere you draw along the x-axis, you can connect to a graph. So x can be anything. There is a graph for it. And the y, again, for y you look at, for range you look at the y-axis. So project everything along the y-axis and you will see that there's going to be a value of y for any value of x. There's always going to be an output for a given input. This one's going to be negative infinity to infinity also. All right, that was easy. Let's take a look at another one. Let's say in this next one, h of x is going to be, suppose that's negative square root of, let's make it negative x, and then minus 2. Let's throw in a negative 2 in here. So the just square root of negative x. The basic function, okay, basic function f of x is root x, correct? So what is f at negative x? F at negative x is going to be square root of negative x. That's when you change x with negative x. All right. And we already know this will cause a reflection about y-axis. We know that part. How do we know that? If you come up here, and there you go. F of negative x, reflection about the y-axis. So we know that. And what else? So let's do that one. And then negative 2 here. So this part of it itself is going to be, again, if f of x is root x, f of x plus k, in this case, k is negative 2. So f of x minus 2 is going to be root x minus 2. K is negative 2. So this thing is going to shift. It's going to be a vertical shift. And it's going to be down, right? Down 2 units. Again, how do we know that? If you come up here, right in the beginning, that's what we talked about there. Okay. And let's now actually graph this thing. So the basic graph was a square root, right? Suppose this is square root of x. Square root of negative x is going to be a reflection. That's square root of negative x. And then minus 2 will drop this graph down 2 units. So let's say 1.0, we can trace that point, bring it down 2 units. So what used to be at 0, 0 is now here. And redraw this graph, the one that's reflected. And that I'm just going to actually, there you go, redraw it like this. And that's going to be the graph of h of x. Now, what about the domain of this one? Domain of h is going to be, again, if you draw anywhere along the x-axis, there is a graph here, 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 here. So looks, but notice there's no graph here. So if I go on to positive x values, there is no graph to connect to. Therefore, my x values are going to go from negative infinity up to 0, or including 0, right? Because the square root of 0 is 0, 0 minus 2 is negative 2, and that's indeed this point right here. That's the domain, and range is the range of function here. The graph starts at negative 2 right here, and it moves to the left. So it's going to go from negative 2 to infinity. For domain, we look at x from left to right. For range, we look at y from south to north, from bottom to top. And there we have that one. That's square root of negative x minus 2. Now let's take a look at, again, one more example. Notice I haven't done any horizontal compression or stretch. Usually with algebraic functions, that's my personal experience, it's very difficult, and there's actually more ways you can, what seems to be a horizontal, let's say, compression or stretch, could be thought of as a vertical compression or stretch, depending on how we work the function. I'll give you an example of what I mean there. That's why those are best done, the horizontal compression, horizontal stretch, those are best done with trig functions like sine and cosine. So maybe once we get there, I can remind myself to do something with horizontal compression with the graph of trig functions. All right, let's take a look at this one. Now again, for this one, the basic function is a cube function, right? The underlying function. So if I look at f at x plus 1, that's when you replace x with x plus 1. X plus 1 cubed. But then f of x plus 1 is f of x minus 1. And this is f of x minus h form. Therefore, h is -1. Okay. And h is -1. H equals -1 less than 0. So it's going to gonna shift left, right? Horizontal shift, that is. Horizontal shift left. And how many units? 1 unit. Right? Absolute value of -1. 1 unit left. And again, you can see it in here. What makes x plus 1 0? -1. So h is -1. H is always what makes inside the function 0. So far, this is what we know. We know that if I work with the basic cube function, and what does basic cube function look like? Again, we can grab this from our library of functions. Right? This is what the basic cube function look like. Again, previous lecture, lecture 4, explains these. So we're going to horizontal shift to the left 1 unit. So I'm going to go and exaggerate my 1 unit. So clear separation there. And just redraw this. And here I have that one. At this point, this is x plus 1 cubed. See how I can trace it? So there is a shift to the left 1 unit. Everything shifts to the left. Everything shifts to the left 1 unit. Okay, and then what about negative in front? This one. And negative in front. So that's going to be like negative f of x. And negative in front causes a reflection about the x-axis. So this part of the graph is not going to be down here. Correct? So I'm just going to redraw that part here. And this portion of the graph actually going to go up here because of the reflection. So I'm just going to reflect this one like that. Okay, and at this point, the red, this is actually negative of x plus 1 cubed. Perfect. All I got to do is do -1, and that -1, a number that is away from the function, that acts as a k in our general form. Okay, and k, again, is the very beginning of our lecture. K was this one. K positive, vertical shift. K negative, K positive, vertical shift up. K negative, vertical shift down. K is -1 here. So the red graph now is going to drop 1 unit. Remember, this was -1. So it's going to drop 1 unit. Let's say that's right in here. I'm going to drop 1 unit. And redraw the red curve. This time I'm just going to make it solid. Right? And that is the final graph. You see that? So this is called, again, transformation of functions, graphing using transformations. Everything we've done here was rigid transformation because we did not scale it. We did not do a vertical stretch or horizontal stretch or anything like that. And so far, in fact, I haven't done any stretching, horizontal or vertical. Okay, now let's take a look at, for example, a simple something where you have to do, let's say, a vertical stretch or compression. Suppose I have y equal 2x squared. So this one, the underlying function is the parabola, right? It's going to be in our library of functions, and this is a basic parabola. Correct? Now, the factor of 2, this is 2 is bigger than 1, so it's going to be a stretch by a factor of 2. Stretch by a factor of 2. Now, it's kind of hard to show a stretch by a factor of 2 on mine, on my graphs, but here's how I can kind of justify it. Suppose I have this blue dot, this point on the graph. The height or ordinate of this point is going to be twice, right? Because we're stretching it. So the height's going to be twice because that factor of 2 in front. So this point is going to be now up here. Well, a point that's here is going to go up here now, right? Twice the height. And then if I redraw this, that's what this graph's going to look like, correct? Suppose that's where it's supposed to be. There you go. So that's how that vertical stretch is going to look like. The vertical stretch typically gives the graph of the function that narrowing effect. So the graph of this parabola is going to be narrower than the basic parabola, the one that we started with. It's called basic. Okay, and that's how you work this one. Now, what if that was, let's say, 1/3? Then I'll just make the ordinate or height of the graph 1/3 of its original value. So again, the vertical compression this time gives the graph a widening effect. So for instance, let's say I have 1/3 x squared. If this is the graph of now, let's say x squared goes like that, 1/3 x squared. So whatever this point is now 1/3 what it used to be. And redraw it. This point 1/3 what it used to be, and redraw it. And you can see now this is what I meant by a widening effect. You see how the graph is wider around the vertex, around the low point. So this is 1/3 x squared. That's what the compression is. You compress it. And the original was x squared. So less than 1, there will be a compression, the widening effect. Greater than 1 will give it a narrowing effect. Now, I did mention about horizontal compression with algebraic functions could be thought of as vertical compression or stretch. Let me give you an example to clarify what I meant here. Suppose my function f of x is absolute value of 2x. Okay, let me go g of x here. Now, so clearly my basic underlying function is the absolute value function, correct? Okay, and we know what the graph of that looks like. So I'm going to make this graph. And here is 2x. Okay, and suppose this point is, let's say, when x is, this is the basic one, right? So when x is 2, this is 2, right? This is y equal absolute value of x. So whatever x is, so is y. And if x is even -2, that's also -2 and 2. All right. Now let's take a look at the graph of absolute value of 2x. So for this one now, I can think of g of x as f of, related to f of 2x, couldn't I? Right, put 2x. What does that mean? F of 2x means replace x in the absolute value by 2x. So you see that? I get exactly what I got. Now based on f, and so this will actually work exactly like f of a of x. And remember up here, we mentioned if a is in parentheses with x, and we have either a horizontal stretch or compression, correct? In this case, a is 2, so I would expect a horizontal compression of the absolute value, right? Keep in mind. And I'm going to write that for you. So this, I'm going to have a horizontal compression by a factor of 2. Okay. Now, let's plot a point or 2 points on the graph of absolute value of 2x. So for instance, let's say when x is 1, when x is 1, I'm doing g of x. When x is 1, 1 times 2 is 2, so y is going to be 2. Correct? And there you go. Therefore, 1, 2 is a point on the graph of absolute value of 2x. Another convenient point would be when x is -1, 2 times -1, -2, absolute value of 2 of that would be 2, so that's -1, 2. Good enough? And now I can actually graph this one. And of course, over the unrestricted domain, this is going to go forever, right? So you really need to put arrows here. But I figured y'all know that. There you go. And so does this one. So all of these go indefinitely, but my focus is on these points. Okay, so notice now we compress this in a horizontal direction by a factor of 2. So there you go. That's the horizontal compression in that direction, right? Cool. Now, this is what I was trying to say. I said for algebraic expressions, for depending on the function, not all of them, but some, including this one. A horizontal vertical compression or stretch could be viewed as a horizontal vertical stretch. Instead of horizontal, we have vertical now. And here's how it becomes vertical. So I'm going to start with my original function. This time I'm going to view this as a vertical stretch. And check this out. How? Remember, we agreed on horizontal compression. That's done. We got the graph. We are done. Now let's review this one. 2x. Now I can manipulate this using rules of absolute values. Absolute value of 2x means absolute value of 2 times absolute value of x. Of course, absolute value of 2 is 2, so that's 2 times absolute value of x, isn't it? And this is now in the form of a f of x. You see that? Up here, it was in the form of f a of x. Now it's in the form of a f of x. True? And keep in mind what I said earlier in here. This is our rule. In general, that's not true. We cannot do this. We cannot be brought out because it's not a factor. So in my very specific example, this actually can be done. And there you go. Now, because I have a constant multiple of a function, a number outside a times f of x, let's go back up here. What does a do? You see that now? We just said it was a horizontal compression, but this is actually now a is 2. We have a vertical stretch. So that is why with algebraic expressions, these horizontal stretch and compressions are tricky. Vertical compression and stretches are a little easier. And sometimes you cannot differentiate between the two, just like my example. Now let's do this graph. Of course, the answer shouldn't change, right? Remember, this point was 2, 2. I'm not going to put the arrows on, okay, folks? I'm just going to go with what I have here. So this is going to be -2, 2. This is -2, and this is 2, and there's 0. Here's x and y. Okay. Now we're looking at 2 absolute value of x. So let me plot a couple of points. I'm going to let x be 1. Okay, let x be 1. When x is 1, in here, absolute value of 1 is 1 times 2 is 2. So this point is now 1, 2. And when x is -1, absolute value of -1 is 1 times 2 is 2. And there you go. I get point -1, 2. And then I can connect my dots. And there you go. Check one. Check out these two graphs. They are exactly the same. You see that? Now this time I'm going to view this as a vertical stretch by a factor of 2. And remember, the effect of vertical when the factor is greater than 1 That vertical stretch gives it a narrowing effect. When the factor is between 0 and 1, it gives it a widening effect. So the graph actually widens, and in this case, it narrows, right? So here's a case where we have a narrowing effect. This time though, if I put my arrows like I did up here with the horizontal compression, this time I have a vertical and sorry, my points didn't align. I didn't realize that just now. There you go. And there you go. My coordinates are not exactly equally spaced, but there. You see that? This point has moved up here. This point moved up here. So my arrows are now pointing up because I'm thinking about vertical stretch. So now I have a vertical stretch by a factor of 2. Isn't that cool? Vertical stretch by a factor of 2 is the same as a horizontal compression by a factor of 2. Okay. And there we have it. That's again just specific to this example that I made up. Alrighty. Again, going forward now, we tend to graph things this way. One thing you don't want to do, everybody, you do not want to plot points. Okay, so if by any chance you're doing this x, y, -2, -1, 0, 1, 2, whatever, you're missing the whole point of this lecture and the whole point of what we're about to do in the future. So we really want to do this using transformation of the basic functions, and that's what we have done. Okay, so hopefully this was useful to all of you, and we are done with this chapter, by the way, functions and their graphs. So everything that we learn, of course, is cumulative, or we're going to take that cumulative knowledge with us to the next chapter and use these concepts over and over in later lectures and later sections. So with that, we are done with this lecture. Thank you for watching.